Right, welcome back. This is my Formalising Mathematics 2022 course, and I'm going to prove the Hilbert Basis Theorem over a sequence of videos. So let's start with making a little bit of API. This is various bits and bobs about the degree of a polynomial. So the first thing that we want is that we would like to make the submodule. We've got a polynomial ring here over a ring R, and we'd like to make the submodule of that polynomial ring consisting of polynomials of degree at most n. So we need to check that that's a submodule. So let's look at the axiom. So basically we're going to have to learn about the API for nat degree, which is the degree of a polynomial as a natural number. So the first goal is that 0 has got degree at most n. So let's see if we definitionally simplify what that boils down to. You see the degree of the nat degree of the 0 polynomial is defined to be 0. So we just have to prove that 0 is less than or equal to n, and I would imagine that will be somewhere in the library. There we go. It's exact 0 len. And now we have an error because we can remove that sorry. The best kind of error. There are no goals to be solved. And now, of course, exact works up to definitional equality, so we don't need the definitional simplification. And then begin exact end cancels, right? Begin end puts you in tactic mode, and exact puts you back into term mode. So we should just be able to do this. There we go. That looks like that's worked. I've got no errors. Right, add mem. So what have we got here? Intros, PQ, PQ, and now what else are they called? I guess HP and HQN. We have the hypothesis we have two polynomials P and Q, and the hypothesis that their degrees are both at most n, and we've got to prove their sum has got degree at most n. We're just checking the axioms for a submodule. Right now we're checking the axioms for a subgroup. An additive subgroup, but the next one will be more module related. So what have we got to prove? I mean, if I just do dsimp at start, we can see what we actually have. We have the degree of P is at most n, the degree of Q is at most n, and we want the degree of the sum to be at most n. So we need some statement about the degree of the sum of two polynomials. So let's just do hash check. We're in the polynomial namespace, so nat degree add or something. Let's see what we got here. So there's various things, and this one here sticks out because we're proving an inequality nat degree add LE. So what's this one? Nat degree add LE says that the degree of P plus Q is at most the max of the degree of P and the degree of Q, so that's going to work. So we're going to do transitivity, right? The nat degree of P plus Q is at most the max of nat degree P and nat degree Q, and that's clearly at most n because both of nat degree P and nat degree Q are at most n. So this is refine LE trans and then nat degree add LE. I'll just leave it like that and then I'll put a comma. So now what's the error? You see it says nat degree LE, you didn't tell it, so you read the error. It's nat degree LE, it was expecting two polynomials P and Q, so that's fine, we can give it P and Q. There we go. And now it compiles. And now this is nothing to do with degrees of a polynomial anymore. You see, we've used the API nat degree add LE. Now this is just a question about natural numbers. We've got two natural numbers, D1 and D2. And we know they're both at most n, and we need to prove that the max is at most n. So we've got to prove the max is less than or equal to something. So it'll be called max LE if or something. We have max LE. So we could apply max LE. Does that work? Yes, it does. And there we go. So now we have two goals, and they're the goals. They're the goals that we have proofs of already. So this is HPN. Yep, and this is HQN. There we go. And so this apply can now change to an exact because there's no holes. And if that's an exact, then we can take that and just dump it dump it in the underscore, so now we don't need that line, and this refine is an exact now there, and this dsympat star we don't need because exact works up to definitional equality. And then the intros can be done outside tactic mode with lambda, so lambda pq hpn hqn begin. Now we don't need the intros, and now begin exact end cancels, so we can get rid of the begin, we can get rid of the exact, and we can get rid of the end. And we got rid of slightly too much, didn't we? What did we? Let's try that again. There we go. Let's leave that L there. And there is a term mode proof of add mem primed. So now what's next is small mem primed. So again, I can intro C and P and HP. Oh, HPN if you like. And now I've got to prove that C small p has got degree at most n. So I want something like it's going to be nat degree small. Have we got any nat? There we go. We've got nat degree small LE. So we can do the same thing, right? We can do refine LE trans nat degree small LE and then underscore and see what we get. And now we have an error. Our nat degree small LE wanted A and P explicitly, so we can give it C and P. And now this works, and our goal has been reduced to P dot nat degrees at most n, and that's definitionally HPN, right? If I do dsympat star, dsympat HPN, now you can see HPN says exactly what this goal is. So HPN can go there, and we can get rid of that, sorry, and we don't need the dsymp, and this is lambdas, lambda CP HPN, and then we don't need the refine, and we don't need the end. There we go. So there's a very, that's sort of a super golfed definition of M. So now rather easier is this mem M if. It says F is in this submodule of polynomials of degree at most n, if and only if the nat degree of F is at most n. And that's just definitionally true, right? Those things are true by if dot, I could do exact if dot refl if you like. If dot ruffle, I think it is. Yes, exact if dot ruffle, but I mean refl will also do it. And that's because F is in the submodule is defined to mean F is in the carrier, and F is in the carrier is defined to mean F is in the set of polynomials which have got nat degree at most n, and F is in that set there is defined to mean nat degree of F is at most n. So that's why that works. Next we have L coef, so this is polynomial.coef, but slightly beefed up, so it's an R module homomorphism. And the thing we need is this thing here, nat degree LE if coef x0. So maybe we should rewrite so we don't actually see nat degree LE, because F is in MRN is defined to be nat degree F is LEN, but that's not a syntactic equality, and so this thing rewrite works up to syntactic equality, so it doesn't work, you see. So what we need to do is we need to rewrite this thing we've just defined, if there, and now you see that unrolls to F dot nat degree is at most n, and then we see we can rewrite this, and so this says the degree is at most n if and only if all the coefficients bigger than n vanish. And we want to do just the same with HFN, right? So we could put this as HFN under the goal. And we could also rewrite this. In fact, we could just rewrite them both. There, comma, this thing here. There, and now get rid of that junk line. So now what's going on here? We've got to prove, I don't know what, n is not a nice, n feels like, I don't know, let's just do intros I, H, I. H, H, N, I, there we go. No, that's a intros I, H, and I, there we go. So we have I are natural, and the hypothesis that n is less than I. And so we want to prove that the coefficient, so the idea is that we're looking at the coefficient of I, but I is a polynomial of degree at most n. So this should vanish. And we're going to be able to do this using HFN, right? HFN says, I mean, we could specialise HFN at I, if you like. HFN now says, well, if n plus 1 is bigger than I, then certainly the coefficient is 0, because that's our assumption, right? That the degree is at most n plus 1. So certainly if I is bigger than n plus 1, the coefficient is 0. But the problem is there's this one edge case that we haven't got. Well, what about the problem is if I is bigger than n because it's equal to n plus 1? And in that case, we can just use HF, because HF says the coefficient, the n plus first coefficient is 0. So we need to do, I guess one way of doing it would be, there's going to be a lemma that says n is less than I if and only if n plus 1 is less than or equal to I. So we could rewrite LE if, what's that going to be called? Sorry, LT if, right? It's going to be here somewhere. It's probably nat.lt if, because it's specific to, oh, here we go, there. They'll be rewriting that to HNI. And so now we know that n plus 1 is at most I. So now we know that either n plus 1 equals I. So there'll be a lemma that says LE, if you're less than or equal to something, then you're either equal to it or less than it. And that's called I don't know, LE if LT or EC or something. There it is. There. So now we've done that rewriting, and now HNI is an OR, and we can do both the cases, right? So we do R cases HNI with whatever, with HNI or HNI. That'll do. And now the first one, it's just we can use HFN now, right? Because we're trying to prove that f.coef I is 0, and we know that n plus 1 is less than I. And so this would be exact HFN, HNI, I guess. That looks good. And then this one, this is going to follow from HNF because n plus 1 equals I. So you feel like we should kind of rewrite we should rewrite HNI at HF. That might work. But the thing is, we don't need to do that. We don't need to do that specialization, do we? We can do that specialization here, right? And you can see that there's no I. There's no I anywhere, right? I is just an arbitrary natural number that we don't know anything about. And so in this situation here, we know that n plus 1 equals I, so we can use that as the definition of I, and that's when you can do this REFL trick here. And so now we don't have to do the rewrite. The rewrite's done for us already. So this should be exact HF. Again, for definitional reasons. The definition of L-coef is it's equal to coef. Right? It's just L-coef is a linear map and coef is the bare function. So this should be exact HF. And it is. So there's that. Now we've got one left, which is nat degree x power LE. So the thing you need to know about nat degree is we've got polynomial dot nat degree x power, it'll be called, or something there. Polynomial dot nat degree x power. It says that the nat degree of x to the n is equal to n. So why are we proving that it's less than or equal to n? And the problem is, look, you can see, we're going to use that, great. So why don't we apply LE of EQ? Now we've got to prove they're equal, and so now we can just apply this, right? And we get an error. Let's read the error. Like, it doesn't work, but why doesn't it work? It says it failed to find a proof that R was non-trivial. Well, we never assumed that R was non-trivial. And the point is, if R is the trivial ring, the 0 ring, then x to the n is just the 0 polynomial, because there's only one polynomial. There's only one polynomial over the 0 ring. It's the 0 polynomial. And the nat degree of the 0 polynomial is by definition 0. So this goal is not actually solvable now, you see. So what was the error? The error, we need to split into two cases, right? Either the ring is non-trivial or it's the 0 ring, and we need to deal with the 0 ring separately. So we want to do cases on subsingleton or non-trivial R. there. And now this is the sub-singleton case, so let's worry about the sub-singleton case later. And now this is the non-trivial case, and now you see we've got this hypothesis that R is non-trivial, so now this should work, right? But you apply and it doesn't work, and it says, oh look, I can't find a proof that R is non-trivial. And we're like, Lean, the proof that R is non-trivial is right in front of your nose. But the thing is, it's right in front of your nose in the sense that it's in the tactic state, but it's not in the local context, right? If you look at the definition of polynomial.nat degree x pow, you can see that this this definition of non-trivial is in square brackets. And square brackets means the type class inference system has to find that. And the type class inference system doesn't look at the tactic state. It just looks at the type class inference system. So when we're doing cases here, we need to add these things to the type class inference system by putting cases I. There, and now you see it's worked. Right, now the apply has worked and goals are accomplished. So that's good. And in fact, we could do, I guess we could just do exact LE of LX, this thing here. Oh, it didn't work. Oh, is it? Oh, because it needs to know something about n or something. There we go, that's worked. And now what about this case here? Well, now we have in the type class inference system the fact that R is a sub-singleton. And there'll be a lemma that says if R is a sub-singleton, then the nat degree of everything is 0. So what will that be called? Nat degree of sub-singleton. There it is, right at the top. So rewrite nat degree of sub-singleton. And now I've got to prove that 0 is less than or equal to n. So that will be library search. It's exact 0 len. So there you go. So that... Oh, I should put the bracket there. Good style. There we go. And so that is the proof of nat degree x power LE. And that is the end of the first sheet. Thanks for watching.